All right, so as I like to try and do as often as I possibly can, this is going to be our video on projectiles and angles. Quite honestly, there is not going to be a whole lot in this video that's going to deviate from what we've already done. Projectiles and angles and projectiles done fired horizontally are going to follow the same two basic principles. And I actually want to highlight those two principles right off the bat. So whether or not we're looking at what we can refer to, oops, let's get rid of this, whether or not we're looking at something that we can refer to as a horizontally launched projectile, or we're looking at a projectile that was fired at an angle, they're going to follow the same basic principles. At some point, you're going to have to solve for time. Right? How long does gravity allow this thing to be airborne? And in the second step for our horizontally launched projectiles, we then took that value for time and we applied it to our constant motion and wrote out that Vx is equal to dx divided by t. And this is how we were able to find the range of all of our horizontally launched projectiles, right? That time is determined by gravity. Gravity is what allows it to be airborne, and the moment gravity has pulled it completely out of the sky, just like the bullet fired and the bullet dropped in that Mythbusters video we watched, it's gravity that determines how long it can be airborne and therefore how long it can travel left to right at this horizontal direction, this horizontal velocity that's usually provided at the beginning of the problem. Well, we're going to have the exact same sort of thing happen here. There's going to be a portion of this problem where we've got to solve for how long gravity lets this projectile being launched at an angle be airborne for. And after we know how long gravity lets it be airborne, our last step is going to be the exact same step we've done before. The only difference now, just like the problem that I started showing at the beginning of this for assignment 5, projectiles at angles, the only difference is that this is measured from some angle from the horizontal and it has some sort of initial velocity supplied to it that is not perfectly horizontal. So I'm going to take that vector that was provided in the example and redraw it here. So we start at 60 meters per second. This is at a 60-degree angle from the horizontal. And this projectile is going to follow, let me do it in a different color. This projectile is going to follow this path here, that same parabolic trajectory that we've observed every, soccer ball being kicked across a field, football being thrown across a field, baseball or softball being hit as a home run, maybe a golf ball on your initial drive, or honestly, any of the hits except for a putt. All of these things follow the same parabolic trajectory. And the idea behind this parabolic trajectory is twofold. There are two portions to it. There is a horizontal component to that velocity, which is labeled as Vx, and there will be a vertical component to that velocity, which I will label as V sub 0 y. And again, I'm labeling the y direction with V sub 0, and I didn't do that with the x direction because gravity only works in that vertical direction. So we're going to treat this in green no different than our standard throw-up problems, right? This would be like taking an object, throwing it up into the air for a little ways, and then allowing gravity to bring it back down to its original position. So we're still going to find how long gravity lets this thing be airborne. The only difference is that instead of our horizontally launched projectile problems, where this was essentially a drop problem that we started with, because this object had all velocity that was horizontal, none of it was vertical. It started with 0 initial speed. In this particular case, with projectiles and angles, it doesn't start with 0 initial speed. It starts with some vertical component of this. And so this is going to be more like one of those throw-up problems that we had done before. Now, the only difference between horizontally launched projectiles and projectiles at angles in terms of the steps that you've got to do, right? Finding time is now going to be our second step. Finding that horizontal range is now going to be our third step. The first step is going to be to resolve that vector, right? This is going to be just like assignment 1 and assignment 2 from our assignment 3 or unit 3 packets. That's the idea. So we are going to start by resolving that vector, breaking it down into its x and y components, finding what those are, then treat it like a throw-up problem to solve for time, and then figure out what that horizontal range would be from it. That's really the only change that we're going to encounter here. So let's do that together. Our initial velocity in the x direction, let's go back to using that particular set of colors I was originally doing. So the horizontal range, the horizontal component to this vector, because remember this was fired, it was 60 meters per second at a 60-degree angle. The horizontal component to this, v sub x, can be solved using the same triangle shenanigans that we've always done. So if I've got a hypotenuse and I'm looking for the adjacent side of my angle, I'm going to use my cosine trig function, right? Cosine is adjacent over hypotenuse. I'll write it out in all of its beautiful detail. Cosine of theta is equal to adjacent over h. Right, you're adjacent over your hypotenuse. So when I go to rewrite this and I'm solving for that particular component, this is as simple as 60 meters per second being my hypotenuse, sorry for the bell, multiplied by the cosine of my angle, which was 60 degrees. And I multiply those two values together, I should get a horizontal value of 30 meters per second. That's my horizontal piece to this. Now for the vertical piece to all of this, right? We have our vertical component. We need that initial velocity in the vertical direction. Honestly, it's going to be the exact same thing as what we just did. The only difference is that this is my opposite side to that angle. So knowing the hypotenuse was provided, I'm going to use sine instead of cosine, but this works out to be very, very similar. It's our hypotenuse of 60 meters per second multiplied by the sine of 60 degrees. Make sure that your calculator is in degrees, and we should get a value of approximately 52 meters per second. I think on my actual answer key that you might see online, I've got a value of 51.9 something. So I rounded this one up, but it's about approximately 52. Now, the positive is going to be really, really, really important. Make sure you keep that because remember, this is going up initially. And just like all things thrown up into the air, unless you're traveling at escape velocity, it will eventually come to rest. Its velocity will drop to 0. In this case, it will be in 5.2 seconds. We'll do that in a second. And then turn around, come back down to the ground, right? So that velocity will change in the vertical direction. Your horizontal velocity the entire time will remain the exact same. So your velocity here is, still going up, still going up, still going up. Here, your velocity in the y direction is coming back down. So let's start, and this is why I like color coding it. Let's start by figuring out how much time has elapsed. Time. Gravity is what allows this thing to be airborne. Gravity works exclusively in the y-axis. So just like our horizontally launched projectiles, we're going to start in our horizontal axis. Now, there are multiple ways you could go about solving this particular problem in order to solve for t. I think the easiest equation that you could probably jump into is, let me go back, let me erase that real quick. I started using regular physics notation, is going to be our final velocity is equal to our initial velocity plus acceleration multiplied by time. Now, in this particular case, we know that our initial velocity in the y direction is positive 52. I'll come back to the final velocity here in a second. We know that our acceleration is negative 10 meters per second squared, and we know that time is what we're solving for. So here's something I want to bring up again, and this is something that a lot of us missed on the last exam. It's something that students every year in physics miss. I don't care which version of this equation you go with. There are two possible solutions for this, and both of them will give you the exact same answer if you plug numbers in the correct way. A lot of students want to use, and I totally understand why, the velocity of 0 as one of their velocities, which is fine, but I want you to recall that the velocity in the vertical direction is only 0 at the top of its trajectory, at the top of its flight path, which is halfway through the problem. So if you take this and you rearrange it to be 0 is equal to positive 52 plus negative 10t, and you solve this, time works out to be 5.2 seconds. Be very careful. This is not your total time of flight. This was the time it took to go from 0 to the top. That's what you measured. That's what you're recording. That's what you're doing the math for. The other potential solution is instead of saying, hey, I want this to be 0, you could make this a negative 52, right? Your initial velocity going up in the positive direction is going to be the same as your final velocity coming back down in the negative direction. So you can write this as negative 52 is equal to positive 52 plus negative 10t. And when you do that one, this is going to turn into a negative 104, which is going to give you a total time of 10.4. Notice how it is double. So if you set that velocity at 0, you've got to take your 5.2 and you got to double it. 10.4 seconds in the air. 5.2 up, 5.2 back down. If you want to do the positive and negative 52s, it's a really great way to make sure you don't miss that particular step because it starts here at the beginning of the problem and ends all the way over here at the end of the problem. So it encompasses the entire range of this projectile. I think it's a little bit easier, a little bit more foolproof, but a lot of people really like using 0. Sometimes you have to use 0, to be quite honest. So 10.4 seconds total time in the air. Now we switch and we transition back to, there we go, the x-axis, right? Your last step is always going to be solving in the x-axis. Why? Because our acceleration in the x-axis is 0, right? These are not planes with propellers or jet engines or rockets with rocket fuel. There's no horizontal acceleration here at all. Gravity is the only thing that works in terms of an accelerating factor. It works exclusively in the y-axis. So on the x-axis, it becomes something as easy as vx equals delta x over t. And we can rearrange that because we know Mr. Willis loathes fractions. So we get delta x is equal to vx multiplied by t. You're going to take your 10.4. 10.4 seconds, and you're going to multiply it. Here's where I want you to be very, very, very careful. Notice at no point here have I gone back and used 60 meters per second. 60 meters per second was used exclusively to find those individual pieces. That's another good color I want to go with. Let's go with pink. The horizontal piece and the vertical piece. That is what the 60 was used for. Once you find those, 52 is what got used down here in order to find your vertical component, in order to find time. And you'll notice, I want to go back to blue, that 30 meters per second was my horizontal velocity. That is what I need to use down here. At no point do we go back and use that 60. That's a really, really, really common mistake. So you're going to multiply those two together, and you should get a value, oops, wrong one, of approximately 312 meters as your displacement horizontally. So again, let me go back to this particular slide right here. In our two sorts of projectile problems, the objective, whether you have to resolve a vector at the beginning or not, the objective is to figure out how long gravity allows it to be airborne, either with a drop problem or a throw-up problem. And then our last step I want you to notice is the exact same for all of them. That was really about it. Now, this step right here, if we progress further in assignment number 5 and you get down to, let's say, number 4, this one's not going to work for number 4. The reason it's not going to work for number 4 is we're talking about a baseball player standing about 1.2 meters above the ground. If we set the initial position for that baseball at 0 and he throws the ball and it lands on the ground some distance away, that new position is not where the position ends at 0. This new position down here, right, y sub 0 is 0. Y is going to be a negative 1.2 meters. So be very careful. Your objective is still to find time there for that first step, but you can't treat it like your traditional throw-up problem because the initial and final positions are not at the same elevation. So you got to go back to that super fun quadratic. Right? We're going to use this particular equation. We don't know what that final velocity is going to be. So I'm going to avoid using the equation that contains final velocity. I suppose you could find the initial velocity with which it was thrown up. That's going to be the velocity here that it's going to have. You know that it will accelerate downward with gravity an additional 1.2 meters. You could find that final velocity if you wanted to. That's a boatload of extra work I would not encourage you to do. So number 4, I anticipated being a little tricky, but I want you to notice you're still in step 2. You're finding time. Gravity in the vertical direction is what determines how long this thing is allowed to be airborne. Then it's Vx equals delta x over t, and that's all it needs to be.